My dear students, let me welcome you all to a new edition of physics. In this edition, we'll learn about the black body, what's meant by a black body, and the radiation of the black body. We'll try to explain the radiation of the black body. As a matter of fact, the early scientific theories failed to explain it, but Max Planck managed to explain it. Okay? If you want to know how to explain these radiations, let's get started. Wave-particle duality. First of all, black body radiation. Definition of black body. A perfectly black body, what about it? It is the body which absorbs all of the radiant energy falling on it and reflects none. So let me say it again. Talking about the perfectly black body. It is the body which absorbs all of the radiant energy falling on it and reflects none. It is an excellent absorber of radiant energy as well as an excellent radiator. A black body in general can be considered as an enclosure from which no energy can escape once it has been received by it. It can be considered as an enclosure from which no energy can escape once it has been received by it. And we've got something important to mention here, important hints. When a black body is receiving energy from hotter surroundings, when it is surrounded by hotter objects, it is in a position of receiving energy. Okay? When a black body is receiving energy from hotter surroundings, it will heat up quicker than any other body of the same surface area. Let me say it again. When a black body is receiving energy from hotter surroundings, it will heat up quicker than any other body of the same surface area. When a black body is emitting energy to cooler surroundings, when it is surrounded by objects which are cooler than it, when a black body is emitting energy to cooler surroundings, it will cool down quicker than any other body of the same surface area. A perfectly black body emits a continuous spectrum of radiation. Continuous spectrum means, yes, it emits radiations of wide range of frequencies. That is to say, the radiation emitted by a heated black body has a wide range of frequencies. The radiation of the black body which affects the eye as light extends roughly from 400 nanometer to 800 nanometer. Of course, you know how to convert nanometer into meter. It is multiplied by 10 to the power of negative 9. So the radiations that can be seen by the eye, yes, are those which have frequency or wavelength ranging from 400 nanometer to 800 nanometer. Okay. When the black body is made hotter, this is very important. Your attention, please. When the black body is made hotter, when we increase its temperature, what happens to the radiation coming from it? emitting from this black body. When the black body is made hotter, its radiation becomes not only more intense, but also, yes, not only more intense, but yes, not only more intense, but also more nearly white. Okay? For example, if you watch the filament of a lamp, the current through it is gradually increased. So we'll increase the current flowing through a lamp, and we'll watch what happens to the filament of the lamp. The filament of the lamp is considered the black body. It is a little bit strange. Okay, it has nothing to do with the black body. And we'll note the radiations coming out from the filament as we raise the temperature, okay? By increasing the current flowing through it. Okay, the current through it is gradually increased. You will see it begin to glow, a deep dull red, become orange yellow, and eventually appear white. You'll see it, yes, begin to glow, a deep dull red. So its color at first will be red, then it is orange yellow, and eventually it becomes white. Okay, as I said, glow, a deep dull red becomes orange yellow and eventually appear white. It has gone from warm to red hot. Okay, it has gone from warm to red hot and to white hot as temperature increases. In front of you, we've got a diagram that shows the intensity of radiations coming from a black body and wavelengths of each wavelength emitted by the black body at different temperature. First of all, the black body is heated to 4000 Kelvin, then it is heated to 5000 Kelvin and 6000 Kelvin. Okay, and we've got something important here to mention. Your attention, please. We'll take it one by one. Some important facts that can be deduced from the previous curves. Okay, the area between any curve and the wavelength axis, area between the curve and wavelength axis. Okay, what about it? It gives the total energy emitted by the black body at that temperature. Okay, the curves at lower temperatures lie completely of higher temperatures. You can note this, of course. Curves at lower temperatures lie completely inside those of higher temperatures. The maxima, the peaks of the curves tend to move towards, yes, short wavelengths at higher temperature. This is very important. The maximum wavelength, what does it mean? The wavelength at which the intensity is a maximum, what happens to this wavelength? It tends to decrease as we increase the temperature of the black body. So let me say it again. The maxima of the curves tend to move towards short wavelengths at higher temperature. That's to say, as the temperature rises, the intensity of every wavelength increases. As the temperature rises, the intensity of every wavelength increases. But the intensities of the shorter wavelengths increase more rapidly. Accordingly, an increase of temperature causes not only an increase in the total radiation, but also shifts the peak of the radiation curve toward the shorter wavelengths. We've got very important law, we call it, or it is called Wein's displacement law. Now talking about Wein's displacement law. Okay, it states that the product of the wavelength at which the intensity is a maximum, product of this wavelength and the absolute temperature of the radiating body is constant. So we have an inverse relation between lambda maximum and temperature of the radiating object. So lambda maximum times absolute temperature equals constant. We call this Wein's displacement law, and this is very important. Your attention, please. Now we've got two radiating objects. One of them is the sun, and the other one is the earth. Okay, and we'll compare between the radiations coming from these two, black objects. And of course, temperature of the earth is much less than that of the sun. And we'll note the difference. Your attention, please. Temperature of the surface of the sun is 6000 Kelvin. So its peak wavelength, which corresponds to maximum radiation, is about 5000 angstrom. 5000 angstrom is 500 nanometer. Okay, this was about what? Lambda maximum of the radiation of the sun. Okay, temperature of the surface of the sun, 6000 Kelvin. And radiations of the sun lie in the visible region. Almost 40% of the total energy emitted by the sun is in the visible region. And about 50% is in infrared radiation, and the rest is distributed over the remaining spectrum. And what about the earth? Yes, thank you very much. The earth is a non-glowing object whose temperature is far less than that of the sun. So its peak wavelength lies in the infrared region. Note the inverse relation between lambda maximum, peak wavelength, and temperature of the radiating object. Explanation of the radiation of the black body. As I said, the early scientific theories failed to explain the radiation of the black body. The equations of classical physics were a good fit to the black body spectrum at, long wavelengths, but didn't work for short wavelengths. According to the assumption of classical physics, the intensity of radiation should increase as frequency increases. And as a matter of fact, Planck managed to explain it. Yes, I'm now talking about Planck's explanation of black body radiation. The radiations of the black body are composed of billions of quanta or photons. Each quantum is a discrete amount of energy. Each quantum is a discrete amount of energy. The energy of the photon is proportional to its frequency. Okay, energy is proportional to the frequency. It is equal to a constant, yes, h times nu. H is Planck's constant. So E is the energy of the photon. And what about the photon? It is light quantum. Its energy can be determined from h nu. Photon has mass and momentum, so it behaves, yes, like a particle. Electrons, which we call it oscillators, electrons of the atoms of the black body, are responsible for radiating these photons as follows. Electrons revolving around the nucleus can only occupy certain set of allowable energy levels. An electron doesn't radiate energy when it is in one of the allowable energy levels. An electron does not radiate when it is in one of the allowable energy levels. The question is, when will the electron emit energy? To radiate a photon, an electron should make transition from higher energy level to lower energy level, from E2 to E1. Okay, from higher energy level E2 to a lower energy level E1. That is to say, the energy gained or lost by electrons are quantized. So we are right now beginning quantum physics. Okay. Energies of electrons are not continuous, but quantized energies. Energy of an electron, okay, can be determined from the expression nh nu, where n is an integer. It could be 0, 1, 2, 3. It is, yes, an integer. And of course, h is Planck's constant. We've got important hints here. The curves that represent the intensities of radiations emitted by different wavelengths by a black body at different temperature support the particle model of light. This is very important. Okay? And now talking about something very important. It is thermal remote sensing. What about thermal remote sensing? Yes, it is detection of infrared, yes, emitting from black bodies. So, talking about thermal remote sensing. Thermal remote sensing is the detection of infrared radiation. Thermal remote sensing is used in, first of all, mapping and photographing the surface of the Earth by satellites, airborne and terrestrial equipments. Yes, it is used in certain military purposes, such as detecting and imaging moving objects in the night, in the dark at night, by night glasses. We call this night vision. So it has military purposes. Yes, it can be used in medicine, in tomography. Tomography is tumor detection, and embryology also. And there is something interesting here. It is used in criminology. Why? Because the heat radiated by a person lingers for a while in the place where the object, where the person exists even after the person leaves the place. Also, it is used in spotting areas of high heat loss from buildings and detecting hot spots in power cables. And now let's try to solve a problem. A black body at 2000 Kelvin, so its temperature is 2000, emits radiation with peak wavelength, yes, 1250 nanometer. Use this piece of information, this result, to calculate the surface temperature of the star Sirius. If lambda maximum for this star is 71 nanometer, assume that Sirius behaves like a black body. So what rule is to be used? Of course, it is Wien's law. Okay. So we'll use Wien's law. We've got an inverse relation between lambda maximum, the peak wavelength, and temperature of the radiating object. So lambda maximum 1, T1, equals lambda maximum 2, T2. Okay, so it's all easy now. The object, when the temperature was 2000, lambda maximum was, 1250. So when it is 71, the temperature will be, 35,200 Kelvin. Okay. And now we've got a diagram. It is about the radiation coming from the sun and that coming from the earth. We want you to use this diagram to solve the following problem. Okay. The figure showed the curves that represent the intensities of the radiations emitted by the sun and the earth at different wavelengths. If the temperature at the surface of the sun is 6000 Kelvin, calculate the average temperature of the earth. Okay, so we should look for the maximum wavelength, or the wavelength at which the intensity is a maximum for each one of them, and they are shown on the graph. It is 0.499 for the sun, and it is 9.66 for the earth. Okay, and once again we'll use the same law, which is Wien's displacement law. Lambda maximum 1, T1, equals lambda maximum 2, T2. So 0.499 times 6000 equals 9.66. T2, it then can be calculated. It is 309.9 Kelvin. This is the average temperature of the earth in Kelvin. If it is converted into Celsius, it will be 37 Celsius. Okay. And we've got questions. We want to answer this question together, okay? First of all, give reason for the wavelength at which the intensity of radiations of the sun is a maximum lies in the visible region, while that of the earth lies in the infrared region. Lambda maximum of the sun lies in the visible region, but that of the earth is in the infrared region. Okay, according to Wien's displacement law, there is an inverse relation between the wavelength which corresponds to maximum intensity, and temperature of the radiating object, on Kelvin scale, of course. Since the Earth is a non-glowing object whose temperature is far less than that of the sun, So its peak wavelength lies in the infrared region, while that of the sun lies in the visible region. Another give reason, when the current through the filament of a lamp is gradually increased. The current is gradually increased. Why? To increase the temperature of the filament of the lamp. Okay, it begins, the filament, it begins to glow a deep dull red, then it becomes orange yellow and eventually a pure white. Why? Okay, according once again to Vane's law, Vane's displacement law, there is an inverse relation between lambda maximum and temperature. Okay, temperature of the radiating object, which is the filament. So as the temperature increases, wavelength decreases. Okay. Another question, why do the curves of the black body radiation, we call them Planck's distribution curves, why these curves support the particle model of light? And this is very important piece of information. Why do the curves of the black body radiation support the particle model of light, not the wave model of light? According to Planck's explanation of black body radiation, the radiations of the black body are composed of quanta or photons. Each quantum is a discrete amount of energy that has mass and momentum. Okay, so the photon has mass and momentum, so it behaves like a particle. So the curves support the particle model of light. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you.